All right, let's dive in. Today we're tackling something truly wild, an unexpected visitor to our solar system that completely flipped the script on what scientists thought they knew. We're talking about Oumuamua.
That's right. And our source material for this deep dive, it comes from excerpts of a scientific presentation and analysis focused entirely on this object. It's essentially a look at what the community learned or maybe unlearned from its brief visit.
And our mission, well, it's to walk through this analysis together, piece by piece, really understand the key findings, the massive puzzles Oumuamua presented, and, where the science stands now because of it.
Yeah.
This object wasn't just another rock. It genuinely challenged some fundamental ideas.
It really forced a hard look at our assumptions. Definitely.
Okay, so jumping into the executive summary that kicks off the source material, what's the headline takeaway? What's the main point the analysis wants to make right up front?
Well, the core message, loud and clear, is that Oumuamua displayed multiple characteristics and behaviors that simply, they defy our current understanding and traditional theories about space objects.
So the standard explanations we have for asteroids and comets, they just didn't add up when you tried to apply them to this thing.
Precisely, yeah. The combination of observed properties just didn't fit any conventional box.
No.
It kind of broke the mold.
In the big, almost jarring dilemma this presented to the researchers, the source lays it out pretty starkly, doesn't it?
It does. The analysis states this very directly. The object's observed behavior implies one of two possibilities. Either entirely new, unexplained physics are at play, something fundamental we just don't understand about matter or forces in space, or the object has an artificial origin.
Wow.
It's presented as that stark, almost binary choice based purely on the data they had.
So it wasn't just, this is a bit odd. It was more like, this is either something fundamentally new to physics or, or it's not natural.
That's exactly the level of the challenge it posed, yeah. And the source points out that studying Oumuamua also highlighted some pretty significant gaps and limitations in how we currently detect, track, and analyze these fast-moving visitors from outside our system.
Definitely need to be ready for the next one. Okay, let's go back to the beginning then. How was this thing first spotted? The section on discovery and initial observations.
Right, so it was first seen on October 19th, 2017. The Pan-STARRS 1 telescope in Hawaii picked it up. Just another potential discovery at first glance.
But it pretty quickly became clear it wasn't just another asteroid or comet hanging around in our neighborhood.
Exactly. The initial classifications changed rapidly. First, they thought it was a standard asteroid, then maybe a long-period comet. But then rapid calculation of its path showed something unmistakable. A hyperbolic orbit.
Hyperbolic orbit. Okay, remind us, what exactly does that mean in simple terms?
So, think of it this way. Objects bound to our sun follow elliptical paths, right? Like circles or ovals. A hyperbolic orbit is more like a slingshot trajectory. It comes in with too much speed and at the wrong angle to get captured by the sun's gravity.
Ah.
It just kind of swings around the sun and then shoots back out into interstellar space, never to return. That's the definitive sign it came from somewhere else.
Got it. So, not captured, just passing through. But the source really emphasizes a major constraint on the data they managed to get.
Oh, absolutely critical.
Yeah.
They had an incredibly limited observation window, only about 11 days, where they could collect meaningful data before it just got too faint and too distant for even powerful telescopes to study in any real detail.
Just 11 days?
Yeah. Imagine trying to understand something completely new with only 11 days of glimpses. It's tough.
That really underlines the difficulty. So, okay, with that limited time, what could they figure out about its physical properties? The analysis gets into some really strange characteristics here.
It does. And one of the most striking was its shape. The analysis points to a highly elongated form, with an aspect ratio that's the ratio of its longest dimension to its shortest, estimated at around 10.1.
Maybe even more extreme.
10 times longer than it was wide, like a cosmic needle or a really, really thin cigar.
Exactly the sort of imagery it evokes, yeah. Its estimated length was somewhere between, say, 100 and 1,000 meters. Pretty big range, but definitely large.
And dark, too, right.
Very dark. It had a very low reflectivity, or albedo. They estimated between 0.04 and 0.10. That means it reflected only about 4 to 10% of the sunlight hitting it. Quite dim.
And the color, did they get anything on that?
Yeah, it had a reddish hue. Now, that's seen on some objects in our solar system, and it can be consistent with surfaces that have been exposed to space radiation for a long, long time, a process called space weathering.
Okay, now for something really important, especially after it was maybe briefly thought to be a comet. Yes, the absolute lack of a coma or tail. This is key. Despite that initial thought, maybe it's a comet, no detectable cloud of gas or dust, that classic fuzzy halo and tail you see with comets caused by material vaporizing off the surface, was observed. At any point.
None at all.
None detected. And that was a really crucial observation.
And that unusual geometry, that extreme elongation you mentioned earlier.
Yeah, the source stresses this is unprecedented. We just don't know of any naturally formed asteroids or comets with such an extreme aspect ratio. The surface composition, like the reddish color, seemed potentially consistent with space weathering, but that shape, that was unique.
Okay, so a dark, reddish, extremely elongated object zipping through with no tail. That's already pretty weird, right?
Definitely weird.
But the central mystery, the big anomaly that defied easy explanation, that was its acceleration.
This is where it gets really interesting. As it moved away from the sun, after its closest approach, Oumuamua showed this small but definitely measurable acceleration in addition to the expected slowing down from the sun's gravity. It was being subtly pushed away from the sun.
Pushed. Okay, what was the magnitude of that push? How strong was it?
The number is about 2.5 times 10 over centimeters per second squared. Now that sounds absolutely tiny, right?
Tiny, yeah.
But it was significant enough to be measured accurately, and it was definitely more than could be accounted for by just the sun's gravity pulling on it. The direction of this extra push was consistent with radiation pressure. The tiny force exerted by sunlight hitting an object.
So the sun's light was pushing it, like a really faint breeze?
That's the right idea for the direction, yeah. But the magnitude of the push was the problem. For a solid object of its estimated size and mass, the force from solar radiation pressure alone just wasn't strong enough to produce that observed level of acceleration. It shouldn't have been pushed that much by just sunlight.
And here's the contradiction we sort of touched on earlier.
Right. Because for natural objects like comets, this kind of non-gravitational acceleration is usually caused by outgassing, jets of vaporizing ice and dust acting like tiny thrusters pushing the comet around.
What?
But as we just said, there was no detected outgassing whatsoever. Zero signs of those jets.
Let's spend a moment on that lack of outgassing, because the source seems to frame it as absolutely critical. What lengths did they actually go to looking for it?
Oh, they looked hard. There were extensive observations across different wavelengths, specifically looking for signs of water vapor, dust, or any other gas emissions you'd normally expect from an active comet.
Even with specialized instruments?
Yeah, even sensitive instruments like the Spitzer Space Telescope, which is really good at picking up the faint thermal emission from dust particles, detected absolutely nothing that indicated material being blown off the surface.
And the analysis point here is, what's the takeaway?
The source is crystal clear on this. Traditional cometary models rely entirely on this detectable material ejection, the outgassing, to explain non-gravitational acceleration. So the complete absence of any evidence for outgassing, despite that measured acceleration, is highlighted as a fundamental, almost show-stopping challenge to explaining this object using standard natural processes.
Okay, another strange observation relates to its spin. The analysis talks about anomalous rotational stability. What's that about?
Yes. Adding another layer to the mystery here. They managed to determine the object was rotating with a pretty consistent period of about 7.3 hours.
Okay, why is a constant spin strange if it's supposedly being accelerated by outgassing, which we know wasn't detected, but if it were?
Right, well, because those jets of material coming off a cometary nucleus, they usually create torques, basically, twisting forces that change the object's spin rate over time. They can cause it to spin up or slow down erratically.
Ah, okay.
So a constant stable spin rate is not what you typically see in a natural object that's being actively propelled by outgassing jets.
So, the constant spin is inconsistent with the most common natural explanation for the acceleration, even though we didn't see the outgassing anyway.
Exactly. The analysis really highlights this inconsistency with known cometary dynamics. It suggests either outgassing didn't happen at all, which fits the observation but leaves the acceleration unexplained naturally, or the object has some incredibly unusual, maybe perfectly balanced mass distribution that somehow cancels out the torques from any hypothetical invisible jets.
Yeah.
Which seems unlikely.
Trying to figure out where it originally came from also seems to have hit a wall, right? The section on origin tracing limitations?
Yeah, they tried. They attempted to trace its path backward using trajectory calculations,
Right.
Trying to rewind its journey. But they couldn't pinpoint its origin to any known star system. It didn't seem to come directly from anywhere we've cataloged.
Not even using models of galactic motion, like how stars move around.
No, even factoring in the movement of stars and systems within the galaxy didn't clearly identify a likely home region or parent star. This led to some speculation that perhaps it originated from a very, very ancient system, or maybe its formation mechanism was just non-standard somehow.
And there was a practical limitation, too, wasn't there, in pinning down its origin?
Right. Our current astrometric precision, that's our ability to measure positions and movements of stars precisely over vast distances, isn't quite good enough yet to definitively link an object like this back to a specific stellar system based on its trajectory alone. Especially after such a long interstellar journey, the uncertainties just get too large.
Okay, let's circle back to the radiation pressure idea again. The source analysis is pretty blunt in saying that solar radiation pressure alone isn't enough for a standard rock-like object.
Correct. The force you get from solar radiation, it depends very strongly on the object's area to mass ratio, basically. How much surface area it presents to the sunlight compared to how much it weighs, its mass.
And for Oumuamua, that ratio didn't work out.
Well, to explain the observed acceleration just by solar radiation pressure, the analysis showed it would need an unrealistically high area-to-mass ratio, far higher than you'd expect for a solid, compact object of the size it appeared to be. It would have to be incredibly light for its exposed area, almost hollow or extremely thin.
So the models would require some extremely low density or really weird shape to make the numbers work.
Exactly. They'd require densities far, far lower than any known solid natural material or a geometry that gives it a huge surface area relative to its mass. One idea that got floated was maybe it's extremely thin, like a sail or a flat pancake, to get that high area-to-mass ratio needed for the push.
But the source says this contradicts observations and, well, what we know about how things form.
It does. What little could be discerned about its structure didn't really suggest such extreme thinness, although the data was limited. And perhaps more importantly, the analysis knows that we know of no natural process that creates kilometer-sized objects with such incredibly thin, flat geometries. Nature doesn't seem to make things like that.
Okay, so faced with these multiple anomalies, the weird acceleration without outgassing, the constant spin, the extreme shape, and radiation pressure being insufficient for a normal, solid object, the analysis then evaluates several proposed natural explanations. Let's start with the hydrogen ice model. What was that?
Right. This was an interesting idea. This theory suggested Oumuamua could be composed primarily of solid hydrogen ice. The thought was that as it got close to the sun, the hydrogen ice would turn directly into gas sublimate, but without leaving a visible dust cloud. So that could potentially explain the acceleration without a visible tail.
Sounds plausible for the lack of dust, maybe, but the source highlights some critical limitations.
Yeah, the main one is temperature. Solid hydrogen ice only stays solid at extremely low temperatures, like incredibly cold. Much, much colder than the environment Oumuamua was in when its acceleration was actually observed near the sun.
So it should have melted, or sublimated.
Exactly. The analysis points out that such an object, made purely of hydrogen ice, should have completely sublimated, just vaporized away during its incredibly long journey through warmer interstellar space, long before it even got close to our sun. The theory just doesn't explain how it could have survived, let alone its thermal properties near the sun.
Okay, so hydrogen ice seems like a non-starter then. What about the nitrogen ice fragment theory? Similar idea.
Sort of similar logic, yeah. This proposed it was a chunk of solid nitrogen ice, maybe chipped off a Pluto-like exoplanet somewhere else in the galaxy. And like the hydrogen idea, nitrogen ice sublimation could potentially cause acceleration without a visible dust cloud.
Issues with this one? Any problems?
The source has several. First, this theory requires very specific thermal and compositional conditions that seem to conflict with what little spectral data we got and how the object heated up as it passed the sun. It didn't quite behave like nitrogen ice should have.
And a statistical problem as well.
Yes. The analysis also mentions that the sheer statistical probability of an object specifically being a fragment of nitrogen ice from an exopluto, then surviving the immense journey and then happening to pass right through our detection zone, well, it's considered extremely low. Possible? Maybe, but very improbable.
Okay, what about the idea that it wasn't solid at all, but maybe a very fluffy, loosely bound clump of dust, like a cosmic dust bunny? A fractal aggregate? Could that have a low enough density for radiation pressure to push it?
The analysis does consider this. A very porous, low-density structure could, theoretically, have a high area-mass ratio. That part makes sense. But the critical problem identified by the source here is its structural integrity. Could it hold together?
And the answer is probably not.
Exactly. The source argues that such a fragile, loosely bound structure just wouldn't survive the immense stresses and forces encountered during interstellar travel. things like tidal forces from passing near stars, even the cumulative effect of radiation pressure itself over millions of years, they would easily tear apart a loose aggregate.
So the fact that Oumuamua arrived intact and seemed to maintain its shape argues against it being a flimsy dust ball.
Pretty strongly, yes. The model fails to explain the object's observed structural integrity after that long journey.
So, okay, after analyzing several of these natural explanations and finding they all have pretty significant shortcomings or require really improbable conditions, the source then introduces the technological explanation, the artificial solar sail hypothesis.
This is presented as, well, an alternative way to explain the whole suite of anomalies observed, one that crucially doesn't rely on inventing new physics or unknown natural processes. The core idea is that Oumuamua could be an object of artificial construction specifically, a very thin, wide structure designed to act as a solar sail.
And how does that fit the data better?
Well, a thin, lightweight structure like a sail is designed, deliberately engineered, to have an extremely high area-to-mass ratio. That's its purpose. And that is precisely the property needed to explain the observed acceleration purely through the known physics of solar radiation pressure.
Ah, okay. So instead of needing weird physics or impossible natural densities or compositions, you just need the right design for the object itself.
Exactly. With a solar sail design, the completely understood physics of solar radiation pressure can provide that observed acceleration. The analysis notes that this type of technology using sunlight for propulsion is something we understand conceptually, and it's consistent with what one might expect from an advanced spacefaring civilization looking to travel between stars.
And how does this artificial sail idea square with the other anomalies we discussed, like the lack of outgassing or the constant spin? Does it help there?
The analysis suggests it explains them quite naturally, actually. An object propelled by radiation pressure doesn't need to eject material, so there would be no outgassing and therefore no coma or tail. That fits perfectly.
And the spin.
And a rigid, stable structure like a well-built sail wouldn't necessarily experience the kind of random spin changes caused by uneven cometary jets. So a consistent rotation rate isn't surprising for such an object.
So this one explanation seems to resolve multiple, seemingly unrelated puzzles all at once.
It's presented as doing exactly that, yes. The sources section evaluating this hypothesis makes a pretty compelling point along those lines. It concludes that the artificial origin explanation consistently explains all the primary observed anomalies together.
And critically, it doesn't require inventing new physics.
No, and that's a key point highlighted in the analysis. It uses known physics, solar radiation pressure, just applied to a structure, a sail, that provides the necessary physical properties. The analysis goes so far as to state it is the most parsimonious explanation for the combined observations.
Parsimonious, meaning the simplest explanation that fits all the facts.
Essentially, yes. It requires the fewest new, unsupported assumptions to make sense of all the strange data points considered together.
The source also briefly touches on something even more profound. Potential implications for gravitational physics, or maybe even suggesting new physics might be involved beyond just the object's nature itself.
Right. It does raise that possibility, though cautiously. It mentions that Oumuamua's precise trajectory might hint at properties that aren't fully explained by standard gravitational models, or maybe even suggest the presence of exotic matter or modified gravity. That's a much bigger leap, though.
So this single object could potentially, maybe challenge our understanding of gravity itself, or hint at something new there.
That's the broader implication the analysis sort of tentatively hints at, that the object's unusual behavior might be a sign of physical processes we don't currently account for. Perhaps even physics related to advanced technology, forcing us to consider expanding our fundamental understanding of matter and energy in the universe. It opens up big questions.
This whole experience also really revealed some limitations in how we, as a scientific community, were set up to deal with something like this, didn't it?
Oh, absolutely. The analysis points out quite clearly that our current detection systems and observational strategies are largely optimized for finding objects orbiting within our own solar system, asteroids, comets, Kuiper belt objects.
Things that stick around.
Exactly. These fast-moving interstellar objects, just whipping through on a one-time visit, they require a different approach, different search strategies, faster reaction times.
And that limited time window we had, those 11 days, that was a huge handicap.
It really was. It severely limited the quality and quantity of data they could get, particularly crucial data like high-resolution spectroscopy, which is what really tells us about an object's composition in detail. They just didn't have enough time on target with the right instruments.
And this leads to a pretty clear call to action in the source material, right?
Yes, and a very strong recommendation for developing dedicated interstellar object detection programs. We need systems specifically designed to spot these visitors early, ideally when they're much further out, to give us more time, weeks or months, maybe to study them properly.
Now, Oumuamua was the first confirmed interstellar visitor we ever saw. What do the statistical models suggest about how often we might see others? Are they rare?
Surprisingly, maybe not as rare as you'd think. The analysis mentions that current models predict anywhere from 1 to 10 such objects might pass within our detection range every single year.
1 to 10 a year, that's a lot more than I would have guessed. So if Oumuamua was so incredibly unusual, does that maybe suggest we might have a blind spot? We might be missing the normal ones.
It definitely raises that possibility. The source explicitly asks if Oumuamua's strange properties, maybe its shape or brightness variation, somehow made it easier for us to detect with our current survey setup. Meaning, perhaps the typical interstellar objects are different, maybe smaller or less reflective, and we've actually missed others that went by unnoticed.
Potential selection bias in our very first detection.
Could be, yeah. Which means seeing more of these objects in the future is absolutely critical to understanding what the actual population of interstellar visitors really looks like. We need more data points than just N1 or N22 now with Borisov.
Right. And the analysis uses that comparison with 2I Borisov, the second interstellar object we detected, as a really powerful way to underline just how unique Oumuamua was.
It's a very effective comparison, yeah. It's colluded right there in the source.
Yeah.
2A Borisov was detected later, and interestingly, it behaved exactly like you'd expect a comet from interstellar space should behave.
How did Borisov compare directly to Oumuamua then? What were the key differences?
Well, Borisov showed clear, unambiguous outgassing. It developed a visible coma and tail made of dust and gas as it neared the sun. Its composition, which they could determine spectroscopically because they had more time, was consistent with a typical comet from our own solar system, just visiting from afar. It fit the expected picture perfectly.
And Oumuamua in stark contrast.
Zero detectable outgassing or dust. Anomalous acceleration that wasn't explained by outgassing. An unprecedented, highly elongated shape, a composition that remains largely unknown but seemed unusual compared to standard solar system objects. It's classified in the source as unique and problematic, while Borisov is essentially seen as a normal interstellar comet.
That side-by-side really does highlight it, doesn't it? Borisov fit the mold perfectly, while Oumuamua just shattered it.
It really drives home the point. If Borisov is what a natural interstellar comet looks like when it visits us, then Oumuamua was, well, it was something else entirely.
And this leads the analysis to the pretty stark conclusion that our current theoretical models for space objects are simply inadequate, at least when it comes to explaining Oumuamua.
That's the summary judgment presented in the source, yes. It states explicitly that no single natural theory proposed so far adequately explains the combination of all of Oumuamua's observed characteristics simultaneously.
And trying to force-fit the data into those natural explanations requires making multiple, often contradictory assumptions, sort of piling special conditions on top of each other.
Yes, the analysis notes exactly that. Natural frameworks attempting to account for all the data require piling on assumption after assumption, often assumptions that aren't compatible with each other, or that conflict with basic physical constraints or statistical likelihoods.
And they just don't hold up under scrutiny when you look at the whole picture.
The source states, these models fail basic consistency tests when they're weighed against the full set of observational evidence. They might explain one anomaly, but make another one worse, or require something physically implausible.
So, echoing a point from the beginning, the analysis concludes this whole situation demands a kind of paradigm shift.
It does. This level of observed anomaly, resisting all conventional explanations so stubbornly, indicates a need for a paradigm shift in how we approach classifying, understanding, and modeling interstellar objects. Our existing categories and theories just aren't sufficient for what we might encounter.
Now, given the possibility raised, however controversially, about an artificial origin, this object clearly has potentially significant implications for the search for extraterrestrial intelligence SETI.
Right. The source frames Oumuamua as representing the first potential instance of detecting a technological artifact passing through our own solar system, rather than just listening for distant signals.
That would be a huge shift in the SETI field, wouldn't it? Changing the focus.
Oh, absolutely. It suggests that SETI methodologies might need to expand significantly beyond looking solely for communication signals, like radio or laser transmissions, to actively search for passive technological artifacts, probes, sails, debris, whatever that might be, traveling through interstellar space and occasionally pass near us.
Which means developing entirely new methods, I guess. How would you even look for that?
Well, yeah, the analysis highlights the need for developing artifact recognition protocols, essentially figuring out what technological objects might look like in astronomical data, their shapes, their thermal signatures, their non-ballistic movements, and how to reliably distinguish them from natural phenomena. It's a whole new challenge.
And it would definitely impact our estimates of how many technological civilizations might exist out there, the whole Drake equation kind of thinking.
Drastically, potentially. If this object, or future objects like it, were confirmed as artificial, it would imply that technology might be present and detectable in the galaxy in ways, and perhaps the densities, previously not factored into those calculations. It makes the universe seem potentially more active.
Okay, the final sections of the source look forward, outlining what needs to be done next based on this whole Oumuamua experience. What are the key recommendations?
It's a pretty comprehensive list, really reflecting the lessons learned. It stresses the need for much improved observational capabilities. Things like dedicated monitoring systems, maybe new telescopes or surveys specifically optimized for finding faint, fast-moving interstellar objects, and crucially, rapid response protocols to mobilize telescopes very quickly when a candidate is detected.
Getting time on the big scopes faster.
Yeah.
And better instruments seem necessary too.
Definitely. The analysis calls for instruments with enhanced capabilities. Things like highly sensitive thermal infrared detectors to search for even faint heat signatures from potential outgassing or internal power sources, advanced spectroscopic systems for much more detailed composition analysis that we could get for Oumuamua, and improved astrometric precision for tracking trajectories accurately.
What about potentially getting closer? Sending something out?
That's discussed too. There are mentions of proposed space missions concepts for fast interceptor spacecraft, maybe from agencies like ESA or NASA, designed specifically to launch quickly and rendezvous with future interstellar objects for close-up study, and maybe, someday, even sample return missions, though that's incredibly challenging.
Wow.
And international collaboration in both observation and mission planning is seen as absolutely crucial to make any of this feasible.
The data analysis on the theoretical side also needed an upgrade based on this.
Yes, clearly. Current computational models really struggle to make sense of Oumuamua's anomalies. The analysis suggests we need new approaches, maybe using machine learning or AI, to spot unusual patterns in survey data automatically, and developing better statistical frameworks for handling these rare outlier events properly. How do you model the unexpected?
And it's not just one field, is it? It sounds like it requires bringing lots of different experts together.
Critically important point in the analysis. It emphasizes the need for truly interdisciplinary research. We need to integrate insights from astronomy, yes, but also physics, materials science, engineering, astrobiology, and maybe even SETI researchers. New theoretical frameworks are needed that can actually accommodate unexpected findings, supported by dedicated interdisciplinary research programs.
All of that requires significant infrastructure and support, I assume. It sounds expensive and complicated.
Absolutely. The analysis acknowledges this. It points to the need for increased funding specifically for interstellar object research. International agreements for coordinated observation and data sharing are vital. Specialized rapid response funding mechanisms might be needed. And of course, training the next generation of researchers in these interconnected fields is highlighted as an essential infrastructure need.
And communicating all of this to the public, especially when you're dealing with possibilities like artificial origin, that seems tricky.
Yeah, the source discusses the importance of careful and transparent science communication. It's vital to clearly present the uncertainties, the competing hypotheses, natural versus artificial, explaining the scientific method itself, how ideas are tested and discarded, and engaging the public responsibly, perhaps even through citizen science projects. It's crucial, particularly given the potential for misinterpretation or sensationalism.
What are the bigger philosophical questions this whole thing raises, according to the source material?
Well, it's framed in the context of potentially encountering evidence of extraterrestrial technology for the very first time. Even if Oumuamua wasn't that, the possibility forces us to confront what that would mean. It challenges our perspective on humanity's place in the universe. It requires developing new frameworks for evaluating potential artifacts. And it impacts how we view the scientific process itself when faced with something truly deeply anomalous. It underscores the need to be prepared scientifically and psychologically for the next unexpected discovery.
So, pulling together the immediate and long-term goals that come out of this analysis, what should happen next?
Okay, immediate goals include things like a thorough reanalysis of all the existing Oumuamua data, maybe with new techniques or perspectives that have emerged since 2017. Long-term goals are much bigger, significantly enhancing our capability to detect and characterize future interstellar objects, developing much better theoretical models that can handle anomalies, and establishing robust international coordination to be truly ready for the next visitor, whatever it turns out to be.
And finally, the critical assessment summary just wraps everything up neatly.
Yes, the source basically reiterates the main points one last time. Oumuamua was an unprecedented scientific puzzle. Its multiple observed anomalies point strongly towards either physics beyond our current understanding or an artificial origin. And crucially, existing natural explanations are found to be inadequate based on the full observational data collected. They just don't fit all the facts.
And the concluding statement from the analysis, the final word.
The final word is essentially a call for open-mindedness going forward. It states that future research and investigation into interstellar objects must remain open to all possibilities, and that explicitly includes the technological origin hypothesis, given the compelling unresolved nature of the evidence presented by Oumuamua. Don't rule it out just because it's strange.
Wow. What an absolutely incredible analysis of this single, fleeting object. From just a faint speck of light in a telescope, it became something that forced scientists, and really all of us, to confront the very edges of our understanding, and to seriously consider possibilities that, frankly, sound like science fiction, ranging from entirely new states of matter or new physics to, yes, the very real possibility of encountering technology from somewhere else.
It's a perfect example, isn't it, of how anomalies, the things that don't fit our existing models, can be the most valuable drivers of scientific progress. They force us to question our assumptions, to think outside the box.
Absolutely. And it leaves us with this truly fascinating question to sit with, doesn't it? What does it actually mean for our understanding of the universe if, when faced with something this anomalous, the simplest explanation based on known physics requires us to consider that it might not be natural? How does that potential reality fundamentally shift our perspective on our place in the cosmos?
It certainly suggests the universe might be even stranger and potentially more populated with interesting things than we've traditionally imagined.
It really does. Well, thank you so much for providing the source material that let us take this deep dive today and for spending the time exploring it with us. This was fascinating.
My pleasure. It's a subject that definitely continues to spark a lot of debate and curiosity, both within the scientific community and beyond.
I bet. If you listening found this deep dive into Oumuamua as mind-bending and intriguing as we did, please consider giving it a like or share. And definitely let us know in the comments what stood out most to you about this incredible, mysterious object.
Yeah, we'd genuinely love to hear your thoughts on the mystery.
Until the next deep dive, keep looking up.